Hi and welcome back to the class on the practice and pitfalls of studying organic reaction mechanisms. We've now made it to lecture 4 of 5, and this time we're looking at linear free energy relationships. And to tell you how we're doing that, I thought I would share a funny old story from my PhD days, where around the holiday season I was gifted this particular picture. Now some of you may recognise who this is, but if you don't, I'll tell you. This is Louis P. Hammett. He was one of the godfathers of physical organic chemistry, if I can go so far as to say that. And the fact that I was gifted this probably tells you something about how much I loved learning about the Hammett relationship and linear free energy relationships during my PhD. So I think that's quite enough of that photograph. But the reason I show it, of course, is that when we look at linear free energy relationships in the context of physical organic chemistry, there's really no avoiding the Hammett relationship, and that's why that's the leading example for us to understand linear free energy relationships and begin to look at how they can be applied to study reaction mechanisms. Even by the name linear free energy relationships, you would be right in thinking that this can get quite mathematical, and I've put some of the mathematical derivations in here. But in keeping with the theme of the entire course, I've tried to keep the understanding as example-led rather than maths-led. If you've got any particular troubles with understanding this particular lecture, please do reach out to me. I'm always here to answer email queries if you have them. But without further ado, and certainly without any further portraits to show you, please do enjoy lecture 4 on linear free energy relationships. Thank you. Hi, and welcome back to the course on the practice and pitfalls of studying organic reaction mechanisms. This is lecture 4 of 5, and we're discussing the Hammett relationship and linear free energy correlations, or linear free energy relationships. So let's start by defining what is meant by a linear free energy relationship, or LFER, in chemistry. For this, we seek advice from the International Union of Pure and Applied Chemistry, who define an LFER as follows. It's a linear correlation between the logarithm of a rate or equilibrium constant for one series of reactions and the logarithm of a rate or equilibrium constant for a related series of reactions. And that's in the IUPAC Gold Book. So let's consider this definition in the context of the Hammett relationship, something we'll spend the majority of this lecture focusing on. We see the example of a base-mediated ester hydrolysis in this scheme. The graph shows a linear relationship drawn out for a series of data points that represent ethyl benzoate esters with different Aryl substitution patterns. The y-axis shows a logarithmic ratio of reaction rate constants, where the denominator shows that the results are normalised against the unsubstituted ester. The x-axis represents a single descriptor used to quantify the properties of each substituted ester substrate. For now, all we need to focus on is that for a given reaction, we can quantify a linear trend using rate data and some descriptor pertaining to the nature of the related series of molecules in the reaction. The name associated with the Hammett relationship comes from one of the early giants in the field of physical organic chemistry, Louis P. Hammett, who first formulated the relationship that now bears his name. So let's try to understand step by step what the Hammett relationship is and how it was formulated. At the top of the slide, we see an amine-mediated methyl ester demethylation reaction and an associated rate constant lowercase k. Below that, we see the equilibrium and equilibrium constant Ka for the protonation of the parent benzoic acid from where the methyl ester is derived. When the two-dimensional relationship between the rate constant for demethylation and the equilibrium constant for acid deprotonation is plotted, we see essentially no discernible relationship it's a mess of data points spread across 2 dimensions. If we dig into the structures of the esters and acids represented on this plot, we can first remove the aliphatic derivatives that have flexible conformations and properties that require deeper consideration of conformer distributions, something beyond the scope of this particular course. Removing these data points starts to draw back the curtain on something approaching a relationship on this plot. Looking within the Aryl derivatives, we can also remove derivatives with steric influence at the ortho substitution site. Such steric influence has exaggerated impact on reactivity and acidity and requires a more involved treatment, again, not within the scope of this particular discussion. So, once we remove those troublesome derivatives, we're left with something approximating a straight line that can be described using a straight line formula. Before we go any further with the Hammett relationship, consider for a moment where LFERs come from and how they are constructed. We did this on previous slides but didn't articulate it directly. First, the requirements. We need a reference reaction to define substituent constants and reaction constants. What is a useful reaction to use to define the behaviours of the molecules you care about? We also need a reference substituent. This is essentially the process of using a benchmark molecule or substrate against which all other substituent effects are measured. Think of this as setting the baseline or zero position. So, if we look at the chemical schemes in the middle of the slide, we see the reference reaction on top, that being the equilibrium involving the protonation state of a benzoic acid. The reaction on the bottom is the one of interest and is understood in some way by comparing it against how the same substituents affect the reference reaction. The potential energy surface on the bottom left shows a simplified representation of the process of deprotonating the benzoic acid in the reference reaction. The starting acid, HA, has an energy. The deprotonation event has an associated transition state barrier, and there is a combined energy of the products following deprotonation. The equations on the bottom right show the thermodynamic relationship between delta G, the free energy change, and equilibrium constant uppercase K. The difference of differences in the free energy for the unsubstituted reference equilibrium and that for the substituted acid is represented in the last equation. Overall, the reactivity differences can be shown to be expressed in a logarithmic fashion, hence why we talk about plotting logarithmic ratios on the y-axis for plots like the Hammett relationship. The top of this slide shows us the reactions and linear plot we've seen before. Let's now dig a little deeper in order to work towards what we recognise as the Hammett relationship. On the bottom, the equation at the top describes the linear relationship from the plot in terms of the axes in that plot. Note that the expression is in the form y equals mx plus c. In our case, the y term represents the log of the rate constant for the demethylation. The x term represents the logarithm of the equilibrium constant for acid deprotonation. The latter, of course, is related to pKa. If we now express this equation relative to the case for the unsubstituted substrates H, we get the logarithmic difference equation shown in the centre of this slide. Remember that the difference of two logarithmic terms can be expressed as a single logarithm of the ratio of the two leading terms. That allows us to derive our equation still further to that shown in the centre of this slide. The logarithmic ratio on the right is defined as the Hammett substituent constant, sigma. This is the main form of the Hammett equation, or Hammett relationship. Following what was quite a significant segue into deriving the Hammett relationship, let's now try to understand how it can be used. The substituent constant sigma, derived in the previous slide, defined by the benzoic acid deprotonation and equilibrium shown at the top of the slide, can be understood on a scale. The substituent constant sigma, defined by the benzoic acid deprotonation and equation shown at the top of the slide, can be understood on a scale. See the diagram in the centre of the slide. If the substituent on the Aryl ring is H, the equation defining sigma collapses to a value of 0. So x equals H sets the 0 position or benchmark for all other substituent constants. If the sigma value for a substituent is negative, i.e. less than 0, then this signifies an increase in electron donating power for that substituent relative to x equals H. If sigma is positive, i.e. greater than 0, then the substituent constant is more electron withdrawing, again relative to x equals H. Meta and para substituents, unsurprisingly, have different sigma values. Take a look at the examples for sigma values for para substituents on benzoic acids. The more negative value for para-methoxy versus para-methyl suggests the methoxy group in the para position is more electron donating than methyl. With that said, what do you think para-amino would be relative to para-methyl and para-methoxy? If you want to give this question a go or discuss it with a colleague, please pause the video now and come back later for the answer. By revealing the answer for para-amino as being negative 0.66, we see that this is more negative than both para-methyl and para-methoxy. In turn, we can infer that para-amino is the most electron donating substituent of these three considered. Let's look at another example. Relative to para-chloro and para-cyano, what sort of numerical value of substituent constant sigma would you expect for para-nitro? Again, pause the video now if you want to answer this question yourself and come back later to see the answer. Here, para-nitro is more positive in value than either of the other substituents. We infer in this case that para-nitro is the most electron withdrawing of the three substituents considered. We mentioned earlier that meta and para substituents will have different sigma values. Here's a question that can help us understand this. So, relative to the para substituents for each of the three benzoic acids shown, what do you think the values of the meta substituent should be here? Pause the video again if you want to give this question a go. Relative to the para-chloro, meta-chloro is more positive and is thus more electron withdrawing. Because chloro is primarily an inductive electron withdrawing group, we would expect that as the substituent is moved closer to the reaction centre, that it has a stronger influence. The lower positive value of the para-chloro substituent is primarily down to the greater distance from the reaction centre and thus attenuated inductive electron withdrawal. However, halogens, on account of their lone pairs of electrons, are also resonance electron donating groups. In other words, halogens have opposing induction and resonance contributions to their substituent effects that have to be considered when rationalising the results of their presence on observed reactivity. Moving to the cyano-substituted acids, we see that the opposite trend to that for chloro is observed. This time, the meta-cyano group appears to be less electron withdrawing than para-cyano. In other words, meta-substitution has a less profound impact on benzoic acid acidity than para. In this case, the cyano group is primarily resonance withdrawing. In the para position, the cyano group has a more direct influence on the carboxyl group. As an additional challenge, you may wish to draw some resonance structures and curly arrows to remind yourself of why para-cyano should be more electron withdrawing than meta-cyano. If you're unsure how to approach such a challenge, please reach out to me or discuss the question with a colleague. Finally, we see that, like cyano, para-nitro is more strongly withdrawing than meta-nitro. The reasons are similar to those outlined for cyano, and again, you may wish to try to draw some resonance structures to justify to yourself why the para-nitro group should be more strongly withdrawing by resonance than the meta-nitro substituent. So what about meta versus para-methoxy? If para-methoxy has a sigma value of negative 0.27, what might we expect for meta-methoxy? Again, pause the video now if you want to give this question a go. Perhaps surprisingly, the meta-methoxy isn't simply less donating relative to para-methoxy. It actually carries a positive value for sigma, inferring that it is, in fact, electron withdrawing in the meta position. In the para position, the methoxy group, or more specifically one of the lone pairs of electrons on the methoxy oxygen atom, aligns in direct conjugation with the carboxyl group, making it more electron rich by resonance donation. No such alignment is possible for meta-methoxy. In fact, because the oxygen atom renders methoxy as an inductively electron withdrawing group, this is the only mode of electronic influence in the meta position for methoxy. Thinking that methoxy is a de facto electron donating group is perhaps one of the most common pitfalls in mechanistic studies, and specifically in studies involving the Hammett relationship. Let's keep going with these questions. What about para versus meta-fluoro? We can see quite clearly that meta-fluoro is strongly electron withdrawing. It's the most electronegative element. It's not in a position to conjugate with the carboxy group. No surprise that it is electron withdrawing and carries a relatively large and positive sigma value. So think about what para-fluoro should be relative to meta-fluoro. Pause the video if you want to give this question a go, and come back later for the answer. In this case, para-fluoro still has a positive substituent constant, but you'll notice that it is very close to zero. In this case, we have the opportunity to highlight the electron donating resonance contributions of the halogens. Because fluoro sits at the top of the group in the same period as carbon, the two p orbitals holding the fluorine lone pairs are more energetically aligned with the pi electrons in the benzene ring than other halogens. In effect, the electron donating resonance contribution from para-fluoro is larger than one expects for what otherwise appears to be a strongly electron withdrawing group. This is another pitfall to watch out for. People often think that fluoro is the de facto electron withdrawing group, but in fact when it's in the para position, the strong electron donating resonance contribution can be seen quite clearly, and you should always be careful of this. Fluoro versus trifluoromethyl provides a chance to delineate the unique effects of fluoro more deeply. Would you expect meta-trifluoromethyl to be more or less electron withdrawing than meta-fluoro? Again, you can pause the video if you want to give this a go or have a discussion with some colleagues. Here, we see that trifluoromethyl is more strongly electron withdrawing than direct fluoro substitution. Having spent some time calibrating how we understand the substituent constant, sigma, we now need to consider the other part of the Hammett relationship, the reaction constant, ρ. This relates to the gradient of the straight line on the plot that we've seen already. On this slide, we see a summary version of a Hammett plot telling us what we can expect to deduce about the reaction mechanism from ρ in conjunction with sigma. Let's look at the axes first. The x-axis denotes our substituent constant scale sigma. The further to the left, the more electron donating the substituent. The further to the right, the more electron withdrawing the substituent. On the y-axis, we have a logarithmic scale denoting the ratio of rate constants or equilibrium constants relative to the reference reaction, usually where x equals h. Turning to the notes at the bottom of the slide, we see 5 points to take away. Firstly, the magnitude of the reaction constant, ρ, is important, not just the direction of the line itself. If ρ is between 0 and 1, we infer that the substituent sensitivity for the reaction plotted on the y-axis is lower than the substituent sensitivity for the deprotonation of benzoic acids, the standard reference process for the x-axis in Hammett relationships. If ρ is greater than 1, the substituent presents a greater sensitivity to the reaction under study than for benzoic acid deprotonation. In terms of directionality, whether the line slopes up or down, if ρ is greater than 0 or slopes up, the reaction under study is said to be favoured by electron withdrawing groups. As you move right along the x-axis, the y-axis increases, be that for a rate constant or an equilibrium constant. Conversely, when ρ is negative or slopes down, the reaction is said to be favoured by electron donating groups. In the following slides, we'll look at some example reactions that can be understood in part by such a Hammett analysis. First, let's consider the deprotonation of aryl phosphonic acids. Here we are considering the logarithmic relationship of the equilibrium constants for the deprotonation as we would for the reference reaction involving deprotonation of benzoic acids. Note that the deprotonation of benzoic acids is still the reference reaction in this case. When we plot this on the y-axis versus the substituent constants on the x-axis, we see a straight line with a gradient, a positive upward slope of 0.76. We can derive two pieces of information here. Firstly, the value of between 0 and 1 for ρ tells us that the reaction is less sensitive to substituent constants than benzoic acid deprotonation. Secondly, the positive value of ρ infers that the reaction is favoured by electron withdrawing substituents, and that negative charge builds up at the rate limiting transition state. For a deprotonation, we're expecting the build-up of charge at the reacting centre. The fact that phosphonic acid deprotonation is less substituent sensitive than benzoic acids can be rationalised by involvement of the third row phosphorus atom, which has a longer bond to the aryl ring with reduced coplanarity than for the carboxyl group in benzoic acids. Let's return to our earlier example of base-mediated ester hydrolysis. This time, the y-axis is the logarithmic ratio of rate constants, not equilibrium constants. The rho value here is once again positive, but is now much larger than 1. What does this rho value tell us about the ester hydrolysis? And what about the direction or shape of the line? What does it all mean chemically? If you want to think about this, pause the video now and come back later to discuss the answer. Firstly, rho is positive, so electron density builds up at the rate-limiting transition state. Overall, the reaction is favoured by electron withdrawing substitution on the Aryl ring. The rho value being much larger than 1 signifies a reaction in which the substituent imparts a greater influence than the same substituents present for benzoic acid deprotonation in the reference reaction. Note the presence of outliers on the plot and that these are for ortho-substituted esters. Recall here that such substituents do not correlate well in Hammett plots due to exaggerated steric effects in the ortho position relative to either meta or para substituents. If we probe this example a little deeper, you might ask, why is this reaction more sensitive to substituents than benzoic acid deprotonation? One way to think about this is to consider the carboxyl group in the reference reaction before and after deprotonation. The carbonyl group remains intact. For the ester hydrolysis, this is not the case. The carbonyl group is temporarily destroyed when the hydroxide nucleophile attacks the ester. This breaks the conjugation between the carbonyl group and the aryl ring, representing a greater disruption in communication between the reaction centre and the substituents on the aryl ring than was the case for the benzoic acid reference reaction. Note that we have to be a little careful in our interpretation of rho values. Note that rho tells us nothing about the direction of reactivity, only that charge, in this particular case negative charge, builds up at the rate-limiting transition state. Let's now move to a new example. The Hammett analysis for the hydrolysis of substituted cumyl chlorides yields the graph shown on this slide. As a side note, the use of 8+, the logarithmic relationship, is simply to raise the values into the positive y quadrant. This doesn't affect rho or our interpretation of the reaction overall. In this case, the rho value is large and negative, giving a straight line with a downward slope. The reaction is more sensitive to substituent changes than benzoic acid deprotonation. Additionally, the negative value suggests a build-up of positive charge at the rate-limiting step. Overall, we have a reaction that is favoured by electron-donating substituents. You may notice a strange deviation from linearity near the top left of this particular plot. We'll come back to this on the next slide. For those data points, in other words those substituents, that don't sit on the straight line for the standard Hammett plot, they can be shifted to the left in order to sit on the line. This then gives corrected sigma values for those substituents that we can term as sigma plus values. Such corrected terms are needed in cases where carbocation formation is a key mechanistic step. The original Hammett substituent constants are simply not appropriate for such reactions, as those original sigma values do not tell the whole story. There is a similar case for reactions involving the formation of a formal negative charge, sigma minus values, but we will not go into this in detail here. Let's take a closer look at sigma plus. When we begin to interpret this reaction, we can think about why ρ is so large and negative in this case. Turning to the chemical scheme on the right, cumyl chlorides hydrolyze via an SN1 process with rate-limiting loss of chloride to form a tertiary benzylic carbocation. Electron-donating groups in direct conjugation with the emerging positive charge will favour this reaction more than other substituents. In cases where the substituent is able to donate electron density via resonance, the substituent influence is exaggerated still further in such reactions. The top left data point in this plot is for para-methoxy. The effect this substituent has on rate of hydrolysis is greater than anticipated. It sits above the line rather than on it or below it. This is because methoxy accelerates the rate of carbocation formation for cumyl chloride hydrolysis more than can be modelled and accounted for in the original Hammett substituent constant. This is not an easy concept to understand or address, so if you need additional help, please do feel free to reach out to me. Here's another example to keep your mind working on understanding Hammett relationships. For the reaction with the two different electrophiles with styrene, can you derive different mechanisms to account for the values of ρ provided? Remember to stop the video here if you want to give this question a go and come back later before revealing the answer. The plots left and right show representative Hammett plots for reactions with the sulfonyl chloride and molecular bromine respectively. Both linear plots have negative ρ values, so both reactions are favoured by electron donating groups, and the rate limiting step may have a build-up of positive charge at the reaction centre. Looking more closely at the reaction with the sulfonyl chloride first, this reaction had the more modest ρ value. We might therefore hypothesise the rate-limiting formation of a three-membered cationic species, but the positive charge is not centred on the benzylic carbon and therefore is not in immediate conjugation with the Aryl ring and its substituents. We need to compare this thought process to that for the bromination. For this alternative reaction with the same series of styrene derivatives, the ρ value is significantly more negative in value. The substituents have a greater impact on reaction rate than for the reaction with the sulfonyl chloride electrophile. Why is that? Here we might present an alternative mechanistic hypothesis wherein the rate-limiting attack of styrene on molecular bromine leads to the formation of a naked benzylic carbocation derivative that sits in direct conjugation with the Aryl ring, communicating directly with the substituents. Electron-donating groups would accelerate this reaction more than in the case of the reaction with the other electrophile, where no such carbocation was thought to be formed. Keeping the handle turning on examples, look at the Hammett data associated with this substitution reaction, where a brosyl leaving group is replaced by an incoming acetate anion. The Hammett plot shows a negative sloping curve that deviates from linearity for electron donating substituents. What might you deduce about the mechanism or mechanisms here, given this particular information? Pause the video here if you want to give this question a go in your own time. Firstly, we can see clearly that there is non-linearity in this Hammett plot. This immediately suggests a change in substituent influence or mechanism for electron-rich substrates. Rho is negative, so positive charge builds up at the rate-limiting step. In other words, the reaction is favoured by electron-donating substituents. In this case, we can envisage two mechanisms for the two regimes emergent from the Hammett plot. In mechanism 1, the brosylate leaving group departs in an SN1 fashion, producing a secondary carbocation. The carbocation itself is not conjugated with the Aryl ring, so substituent effects in this regime are modest. In mechanism 2, the Aryl ring directly participates in the ejection of the brosylate group, forming a phenolium cation via neighbouring group participation. This mechanism is switched on by strongly resonance-donating substituents such as methoxy, and thus accelerates the reaction rate to a greater extent than would be expected, hence the deviation from the simple linear trend. If we consider mechanism 2 still further, the phenolium ion created via neighbouring group participation now sets up not one, but two equivalent electrophilic sites of attack for the incoming acetate nucleophile. Having considered the Hammett analysis as the flagship linear free energy relationship in physical organic chemistry, it is important to stress that it is by no means the only LFER in use. The Taft relationship, developed by physical organic chemistry pioneer Bob Taft, is another useful and important LFER in mechanistic chemistry. The Taft relationship accounts for both steric and polar electronic effects in one equation. Two effects described inevitably means two reference processes from which to extract quantified values for these effects. Look first at the chemical schemes on the left of this slide. At the top, the polar effect, denoted sigma star, is taken from the base-mediated hydrolysis of methyl esters, with the reference substituent having R equals methyl. Taft rationalised that the base rather than acid-mediated hydrolysis would be most greatly influenced by polarity rather than sterics. Because the ester and protonated ester differed in structure by a single proton, Taft used the acid-mediated hydrolysis to estimate the steric impact of the R group, assuming lower influence of polarity in acidic medium than for basic medium. Turning to the equations on the right, you can see how the steric term E subscript S is defined, with the rate of base-mediated ester hydrolysis for R equals methyl serving as the reference reaction. For the polar term, sigma star, the equation is slightly more complex and subtracts the effects of the acid-mediated hydrolysis A from the base-mediated hydrolysis B. The combined equation and Taft relationship is shown in the box. Just like rho in the original Hammett analysis, rho star and delta star represent sensitivity terms in the Taft analysis. The table on the bottom left gives us a feeling for the magnitude and direction of the different terms for each substituent R. Note that methyl, not H, is the reference now. For E subscript S, the steric term, more negative values infer a larger, more sterically influential substituent. Compare, for example, methyl versus tertiary butyl. For sigma star, the polar effect, that can be considered in a similar fashion to the Hammett substituent constant sigma. values more positive than 0, the value set for methyl, the substituent can be considered electron withdrawing. Negative values of sigma star are for electron donating polar effects. Note that by polar effects, we refer to the combined influence of resonance, field, and inductive effects in one term. To make these polar and steric terms clearer, consider the scales on the right of this slide. For polar effects, negative sigma star values denote increasingly electron donating groups. Positive sigma star values infer more electron withdrawing R groups. For steric effects, negative E subscript S values denote increased steric bulk. Positive E subscript S values occur for R groups with reduced steric bulk relative to methyl. The Taft steric parameter is not without its flaws, however, and should be considered as situation specific. Note that the Taft steric parameter E subscript S would suggest that phenyl is sterically larger than tertiary butyl. If we turn to cyclohexane A values not covered in detail in this course, as an alternative steric parameter, tertiary butyl is quantified as being much larger than phenyl. If you want to know more about quantifying steric parameters by alternative means, please do reach out to me. In summary, we've used this lecture to discuss the place of LFERs in studying reaction mechanisms. As with all our lectures, this subject is somewhat of a field unto itself, and we have merely touched on the fundamentals in this course. We spent most of the time defining and interpreting the most common LFER in physical organic chemistry, the Hammett relationship, and that is summarised on the plot. The sigma value denotes the electronic effects of a substituent. That sigma value can be corrected for more specialised charge-bearing mechanistic regimes, i.e. using sigma plus or sigma minus. The rho value denoted the reaction constant and describes the sensitivity of the reaction to the presence of substituents relative to the sensitivity for substituents in a reference reaction. We explored deviations from linearity in the Hammett plot, and how that might be interpreted as a change in rate-limiting mechanistic steps. Deviations from linearity go further than described here. It can also relate to changes in entire mechanisms. Finally, we ended the lecture by briefly considering one of the many other LFERs available for use in mechanistic analyses. You might one day even develop your own. So thanks for watching lecture 4 on linear free energy relationships. We're now most of the way through the course with one more piece of the puzzle to fill in. I'll see you back here for the 5th and final lecture. Thank you.